In this problem, we are given a geometric progression where Sn, S2n and S3n, these three numbers represents the sum of n, 2n and 3n terms. Now we need to show that this particular expression holds true. So let's begin. First we will specify the common ratio as well as the first term. So let the first term of the geometric progression be represented by the letter a in lowercase, and we have to present the common ratio in lowercase as well, so let it be represented by r. Now we know that the sum to nth term of a geometric progression is given by the formula a times r raised to the power of n minus 1 divided by r minus 1. So let this be equation number 1. Then S2n, so this will be equals to a times r raised to the power of 2n minus 1 divided by r minus 1. So this represents the sum to the 2n terms. This be equation number 2. And then we have S3n, which represents the sum to the 3n terms. So that will be a times r raised to the power of 3n minus 1 divided by r minus 1. This is number 3. So let's begin from the left hand side of a given equation. So on the left hand side, we have Sn squared plus S2n squared. So we'll replace this value here. So Sn squared will be a squared multiplied to r raised to the power of n minus 1 whole squared divided by r minus 1 plus S2n whole squared. So that will be a squared times r raised to the power of 2n minus 1 whole squared divided by, so there's a r minus 1 whole squared in the denominator as well for both the two terms. Now, so we first will take a squared divided by r minus 1 whole squared as the common factor. So this will get multiplied to r raised to the power of n minus 1 whole squared. So that's r raised to the power of 2n minus 2 times r raised to the power of n plus 1 plus r raised to the power of 2n minus 1 whole squared. So that's r raised to the power of 4n minus 2 times r raised to the power of 2n plus 1. So combining this, we're going to get a squared divided by r minus 1 whole squared. We have r raised to the power of 2n minus 2 times r raised to the power of n plus r raised to the power of 4n minus 2 r raised to the power of 2n plus 2. So what we're going to do, we're going to add and subtract an extra term. So let that extra term be r raised to the power of 3n. So we're going to add this extra term, and we're also going to subtract r raised to the power of 3n from it. So that means we can now rearrange the terms to get a squared divided by r minus 1 whole squared. This will get multiplied to, so we have r raised to the power of 3n minus r raised to the power of n. So we are writing some of the terms minus r raised to the power of 2n plus 1. This will be, let's consider it as a single term, and this will get added to r raised to the power of 4n minus r raised to the power of n minus r raised to the power of 3n plus 1. Now the reason why we are doing this, because we have a squared divided by r minus 1 whole squared. This entire expression, so this is actually the factorization of r raised to the power of n minus 1 multiplied to r raised to the power of 2n minus 1. And the second term, this is the factorization of r raised to the power of n minus 1 times r raised to the power of 3n minus 1. Right. Now we can finally multiply a squared divided by r minus 1 whole squared to each of the terms. So we have a divided by r minus 1 multiplied to r raised to the power of n minus 1 times a times r raised to the power of 2n minus 1 divided by r minus 1 plus a times r raised to the power of n minus 1 divided by r minus 1 multiplied to a times r raised to the power of 3n minus 1 divided by r minus 1. So this is nothing but the sum to the n terms. So this is sum to the 2n terms plus we have sum to the n terms multiplied to sum to the 3n terms. So if we take Sn as the common factor, this will be multiplied to s of 2n plus s3n, which is the expression on the right hand side.